This is 4.1.2 moments of a force. You can recall back from GCSE that the moment of a force is the turning effect of a force, how well a force can make something turn or rotate. So let's set up a seesaw. So we'll put one person sitting on the end and someone else sitting nearer to the pivot. So we've got force 1 from this person, force 2 from this person, a distance to the pivot, x1 from one person, and x2 to the other person. This system is in equilibrium, which means that there is no rotation. About the pivot. So this goes on to the definition of the principle of moments. Which says that for equilibrium, the sum of all clockwise moments must be equal in magnitude to the sum of all anti-clockwise moments. So for equilibrium, the sum of all clockwise moments is equal to the sum of all anti-clockwise moments. Put a box around that definition. It's one you need to know. So a moment is the turning effect and the units for it are Newton meters. Not newtons per meter, Newton meters. The equation for it, moment of a force, is equal to force times perpendicular distance. Now this is quite important. If I write the equation underneath, T equals to F times D. Because force times distance is also work done. Newton meter is also the same as a joule. So the question arises, is the moment the same as energy? The answer is that they're not. And the distincting factor is that for energy or work done, the force and the distance are in the same direction. They're parallel to each other. In the case of a moment, they're perpendicular to each other. Now in high-level mathematics, when you start to learn vectors, there are two types of vector multiplications, which is a dot product and a cross product. For work done, it's a dot product. For moment of a force, it's cross product. For the moment, this probably won't mean anything to you, but it's something you can recall later in your life and start to have more of an appreciation of the mathematics behind the difference between force and work done. So moment and work done. So if the force and the distance are parallel, you don't have a moment. You cannot have a moment. The turning effect can only happen if they're perpendicular to each other. So, if we take the above example with the fat guy with F1, X1 and the skinny guy with F2, X2, if we use the principle of moments, we can construct a relation between the two. So the clockwise moment from the skinny guy is equal to the anti-clockwise moment from the fat guy. So F1 times X1 is equal to F2 X2. And this is only the case because we said they were in equilibrium. If they're not in equilibrium, then these won't be equal to each other. Now the fat guy obviously had a larger force because W equals to mg, so F equals to mg. So if the fat guy had a larger mass, that means he had a larger force. However, that's why he was sitting closer to the pivot. He had a smaller distance so that the product of his force times distance was equal to the product of force times distance for the other person, hence allowing them to be in equilibrium. Now, when solving moments problems, they'll typically be a lot more complex than this. So key thing is always start with the forces. And I'll demonstrate this on the next page. So always start with force. Then, for the next step, state where you're going to take moments from. In other words, choose all possible places that can be a pivot. And you take moments from several places. State where you take moments from. So which is anywhere that could be a pivot. Right, let's look at our first example. So start a new page, please. Type 1. And this is arguably probably the most important one to understand because it will allow you to solve most moments problems. So let's say we have a platform which is suspended by two strings or ropes with tension, T1, T2. This platform is 6.0 meters long. We have a person who's 50 kilograms in mass, standing 2.0 meters from T1 and 4.0 meters from T2. Now you have two possible places of pivot, which are where T1 and T2 join with the platform. If you imagine that you're holding these strings, if you pull on T1 too hard, you're going to rotate about T2. So T2, the point at which T2 is attached to the platform acts like a pivot, and it will rotate around one way. If you pull too hard on T2, then T1 acts like a pivot and pulls along there. So let's mark these 2 points that I'm talking about. So here and here. So these are our possible pivots. These are the places that we're going to take moments from. We're going to assume that the platform has no mass. So the platform itself doesn't have any mass, or it's got negligible mass. So that the person who's standing on it has a lot more mass than the platform itself. Otherwise, usually we'll have to take that into account as well. So this person has a force which is equal to mg going down. And now we have to begin considering the different points. So I said, first of all, consider forces. So, is this platform falling down? Is this platform moving up? It's not moving at all. So if it's not moving at all forces must add up to equal to 0. Which means all the upwards forces and all the downwards forces must add up to equal to 0. So they must be equal to each other. So, consider forces. Platform is not moving. Therefore, resultant force is equal to 0. That means that mg is equal to T1 plus T2. And we can calculate mg because we know that he's got a mass of 50 kilograms. We know that g is equal to 9.8. Then we have to take moments about our possible pivots. Take moments about the different pivots. So, the system is in equilibrium. It's not moving, it's not rotating. Which means that clockwise moments have to equal to anti-clockwise moments. So if we label these as A and B, if we take moments about point A, then the person provides the clockwise moment. If we try to rotate about A, he tries to rotate the system clockwise, and T2 provides the anti-clockwise moment. So let's take moments from A. So from A, the moment from the man was mg times his displacement from A, which was 2 meters. Or we could call that x1. If we relabel this as x1, x2, we can put the numbers in at the end. So from A, we've got mg x1 is equal to the anti-clockwise moment caused by T2, and T2 was at a distance of x1 plus x2 from A. If we go back up, it's x1 plus x2 from point A to get to T2. So mg x1 is equal to T2 brackets x1 plus x2. And we know from our diagram that's equal to 6. Again, we can put our numbers in at the end. Then we can consider moments from point B. From point B, our person is providing the anti-clockwise moments, and T1 is providing our clockwise moment. So this time it's going to be mgx2 is equal to T1 into x1 plus x2. At this point, we have all the necessary information that we need to solve the problem. So let's start putting our values in. So I'll do the moments from A and B. From A, we had mgx1. M was 50 kg. G, I'm going to use 10 because I'm lazy. So I'm going to do 50 times 10 times by x1, which was 2 meters. So mgx1 equals to T2 x1 plus x2. And underneath that, I'll put my numbers in. 50 times by 9.8, which is roughly 10, times by x1, which was 2, is equal to T2 into x1 plus x2 is 2 plus 4, which is 6 meters. And then for B, we had mgx2 is equal to T1 x1 plus x2. So again, we put our values in. So this is 50 times 10 times by x2, which is 4, is equal to T1 times by x1 plus x2, which is 6. So 50 times 2, that's 100, times by 10, that's 1,000. So 1,000 is equal to 6 T2. And here we've got 50 times 4, that's 200, times by 10, that's 2,000. 2,000 is equal to 6 T1. Now we can rearrange to get T1 and T2. So T2 is equal to 1,000 over 6. So T2 is equal to 167. And then here we've got T1 is equal to 2,000 over 6. So T1 gives us 333 newtons. And now we can verify using the first equation we did. mg equals to T1 plus T2. So mg, 50 times 10 is equal to T1, which is 333, plus T2, 167. Fifty times 10, that's 500. And T1 plus T2, 333 plus 167, well, that's also 500. So both of the equations agree with each other, and we've solved the problem. Okay, next we'll do type 2. We've got a pivot. Let's say the total separation is 3.0 meters. And we've got two people sitting on the ends. And each of these separations are 1.5 meters apart. If this person is 50 kg, and the next person is a small child, say 20 kg, this system is not in equilibrium. Because the moments, the clockwise and anti-clockwise moments are not equal. So not in equilibrium. So for this, you need to calculate the resultant moment. And that's the way it's going to rotate. So in this case, even without doing a calculation, you can see that it's going to rotate anti-clockwise. Because the 50 kg person will provide a larger force. They have the same separation from the pivot. Therefore, the 50 kg person will go down, 20 kg person will go up. Generally, this is a much more simple problem to calculate compared to type 1. Next, we'll look at type 3, which is a torque problem. So we've got a nut and a spanner. If this separation is 20 centimeters and we apply a force on the end here of 30 newtons, then we just apply T equals to F times D. And you'll just do 30 newtons times by 20 centimeters. Remember to convert that into meters. So it'll be 30 times 0.02. Sorry, 0.2, not 0.2, 0.2. So again, a simpler problem. Last one is a couple. And couples are when you apply forces in two separate directions on two different sides of a pivot in order that they provide the same moment or moments in the same direction. And that allows easier rotation. For example, the one we're going to look at is in a steering wheel. The reason why you would use two hands on a steering wheel on opposite sides is that it gives you more moments because they act as a couple. One hand pushes down, one hand pushes up. So you get two moments that act together. So here's a steering wheel. It's of a fancy car brand, which is the B-Mobile. If we're going to steer to the right, we apply one force up, one force down, and the pivot is this distance here, or distances, which are the same distance apart. Now, in this case, the distance just happens to be the radius of the wheel, because it's a wheel. So two forces working together. So T is equal to F1x plus F2x. And that's the end of 4.1.2.